Hi, welcome to my first tutorial of Organic Chemistry 1. And in Organic Chemistry, or just in my tutorial, I won't go through the simpler stuff, which is pretty much the first half of the semester. Mainly, I'll go through the biggest and most important thing in organic chemistry, and that is the reactions. And there are about 30 or so reactions in Organic Chemistry 1. I'll go through each of them one by one, but realize in the actual test, it isn't based on each individual reaction. There's going to be a huge combination of reactions. Sometimes you might get 5 at a time, maybe even 10 at a time. And even complex pharmaceuticals can take up to 70 or 100 steps just to synthesize one drug. See, I already made a video of this, but when I was checking it, the sound quality was horrible. And I already had written everything on here. In my next videos, I'll start from scratch. But in this video, uh, I'll explain everything as I had written up. So I'll explain a very simple reaction. This is the addition of HX, which stands for hydrogen halide, to an alkene, which is a double bond. So HX, H is hydrogen, X stands for a halide. And if you don't know what a halide is, it's just group 7 of the periodic table. That's fluorine, bromine, chlorine, and iodine. And as you're moving down, the periodic trend is that it becomes a stronger and stronger acid when you're moving down. But that's Gen Chem stuff, which you should have already learned. So in alkene is a carbon double bond into a carbon. Then, all right. So first of all, this is an addition reaction. But in organic chemistry, there are four types of reaction. These are just something you need to keep in your mind at all times. There is a substitution reaction. In substitution, there is SN1 and SN2, which you should probably learn before watching these videos because it assumes that you already know what SN1 and SN2 reactions and E1 and E2 reactions are. This is an so there's substitution reactions. If you don't know what those are, watch Khan Academy for the basics. There are also elimination reactions, and if you don't know what these are, watch Khan Academy. And there's rearrangements and addition reactions. Each of these are equally complex, so it's just because you have the word addition which doesn't sound as complicated as elimination or rearrangement doesn't mean it's going to be easy. So in this video, I'll cover a similar an easier question or easier problem. This is a addition of that's just the run-of-the-mill alkene to a hydrogen halide. This right here is ethene. Eth, just as a review of organic chemistry, Eth stands for 2. Ene stands for a double bond. So this is ethene is a double bond between 2 carbons. So then you might ask, where does the hydrogens fit in? Well, a carbon can form 4 bonds. That would suffice for the octet rule. So if you know that a carbon, 2 carbons, you have 2 carbons that form double bonds, and that means each of the carbons would have a remainder of 4 or 2 more bonds that it could form. Then the remainder of the bonds, you just fill it in with hydrogens. So then you have an ethene molecule reacting with a hydrogen halide molecule, hydrogen halide. So what happens is the hydrogen halide is an electrophile, or the H of the hydrogen halide is electrophile. The reason it's an electrophile is because of electronegativities. So you can see it from the perspective of an electrostatic map, which is what I've drawn here. It looks like this. Electrostatic maps measure how many the electrons densities. This one has a huge bulge, you see. It's because the halide is very electronegative. And if something is very electronegative, it means that it has a strong affinity for electrons. It wants to pull the electrons toward it. Hydrogen is a very small atom. It doesn't pull really hard, so it gets its electrons pulled towards the halide, which is gigantic relative to the halide. So what happens is the halide or the hydrogen is losing some of its electrons, or it's losing its share of some of its electrons. So it becomes more positive because it has less electrons close towards it. And the halide pulling the electrons in from the hydrogen has more electrons closer towards it, so it becomes negative. This would fit in with the reaction because the hydrogen here is an electrophile. And what electrophiles like to do is it likes to go for electrons because, if you have a magnet, you have a negative magnet and you have a positive magnet. Put those two together and they'll stick together. They'll attract. Same thing here. What double bonds are, or any bonds, between the carbon and hydrogen, or the carbon and carbon, is that you have a region when there is more electrons, more negative. What happens is now you got the hydrogen, which is positive, it's going to float towards these double bonds, and it's going to drag off, pull off one of the bonds of the double bond. So that means this carbon here will only have single bonds. Where does the bond attach to? Well, in this case, because the molecule is symmetrical, and it's very important whether that in this case that the molecule is symmetrical, because if it's not symmetrical, you have a heck ton of new more of other rules you have to follow. Actually, it's just two. There is the Markovnikov and anti-Markovnikov rule, and that will also depend on the reagents you use. But I won't go into any details about that right now. Right now, I'll focus only on symmetrical molecules, so it doesn't matter where the double bond ends up. It could end up on this carbon, or it can end up on this carbon. Okay, so I imagine it looking like this. Say you have a piece of tape here, and then the tape, like a rope, it's like a piece of tape on the end of a rope, and you could throw out the rope, and it would stick to something. So the carbon here, the double bond here, is throwing out its sticky tape. Imagine each end of this bond as the end of a rope. It would throw out its sticky tape and stick it onto hydrogen. But we know that hydrogens can only form one bond. That is something that's from Gen Chem. That's just something you should know by now. Hydrogens can form one bond. But if it has its electrons stuck to hydrogen, then hydrogen has two bonds here. You got one here between, let's see, it could be either one of the carbons, depending on which side you look at. It could be carbon bonded to hydrogen here, or carbon bonded to hydrogen here. Since it's symmetrical, it really doesn't matter. So I'll say carbon bonded to this here. And you also got another bond between the hydrogen and the halide. So you got two bonds, but hydrogen cannot make two bonds. So if you want the reaction to proceed, that means you have to lose one of them. You have to get rid of a bond. So that means the arrows here mean that the electron is moving towards the halide, the X. So what you're left with now is you have this carbon here, which has three hydrogens attached. See, went from two hydrogens to three hydrogens. That's because the electron, the double bond here, one of the bonds, has been given to the hydrogen. So this side has three hydrogens. You could also make it that this side has three hydrogens instead of this side, but it's the same. It's symmetrical, so it doesn't matter. Now this side is this carbon. When one side has three hydrogens, the other side is positive. This carbon is positive. It's called a carbocation, and that's because when you look at formal charges, this is the formula for formal charges. Formal charges is you take the group number minus the number of bonds minus the number of unpaired electrons. In this case, you just have to look on the periodic table that carbon is group number 4, and that's something you should probably memorize. Carbon is group number 4, so it has 4 electrons to start out with. This carbon here is bonded to has 4 bonds. See, 4 lines. So minus the number of bonds, 4. 1, 2, 3, 4. It has no lone pair electrons. So you don't subtract this, subtracting 0. Now you're left with a formal charge of 0, which means this part is stable. There's nothing, no carbocations or no negative charges anywhere here. This side is different. This side, this carbon is bonded to 3, has 3 lines. So it's 4 minus the number of bonds, 1, 2, 3, minus the number of unpaired electrons. It doesn't have any, which means it has a formal charge of 1. 1 plus, positive 1. Well, in organic chemistry, you don't like this sort of stuff. You don't like molecules with a positive charge or negative charge. Well, usually negative charge, you could keep negative charges, but a positive carbocation is unforgivable. You don't want it. So, because it's very unstable and very reactive, and you want to get rid of it. Luckily, well, if you look in the previous step, the hydrogen couldn't form two bonds, right? Remember that? Which means it could have had to give away the halide, which could be chlorine, bromine, iodine, or fluorine. So now you got this is a solution. You got a lot of these things going on. So now you got this halide floating around there, and you got a positive carbocation that is very reactive and doesn't want to stay positive because it's very unhappy. And then you have this negative halide, which doesn't want to be negative. So, what better way to get rid of both of these than for them to stick to each other to react, which is what happens here. So literally, the negative part, the lone electron or the extra electrons of the halide is literally just going to be given to the carbon, and when it's given, it forms a bond or a line. So you know that this side has three hydrogens. This carbon's bonded to three hydrogens. This carbon now has gained the halide from here and the other two hydrogens. Well, we also look at the formal charges now. The carbon here has a +1 formal charge, and the reason is I just explained before that carbon is group number 4. There are three bonds, so it's -1 for each bond. One, two, three, and it's positive. Well, look at this one now. Now this one has it's four. Okay, so it's group number 4 -4 bonds. 4, 3, 2, 1, 0. It has a formal charge of 0. So now this is a stable molecule. This molecule doesn't have any random carbocations around anywhere, and it's very nice looking. So this reaction is called the addition of hydrogen halides to an alkene. You'll need to memorize what they're called because you'll end up doing more than 30 of these reactions in a month. So you need to learn these names, otherwise you'd be totally confused and have no clue what's going on in class. And yeah, so this is the first tutorial, and actually I could read you the remainder of the reactions that I'm going to go through in this tutorial, and there's a heck ton of them. So the first one is called acid or addition of hydrogen halide to a double bond. And actually I made a list of these for my review of my final exam. And you know I'm pretty good at this because I got an A in the class um, with this impossible teacher. So I got then okay. So the next reaction is called acid catalyzed addition of hydroxide. Then you have cold sulfuric acid addition. You have a very important one which you need to learn really well, and I will probably make sure to emphasize is oxymercuration demercuration. You have hydroboration. You have oxidation of trialkyl boranes, which is just an intermediate step for hydroboration. Just so you know, you don't need to learn all this right now. It's just an overview of what you will learn. Then you have electrophilic addition of bromine and chlorine to alkenes. You have protonolysis of alkyl boranes, halo hydroformation, syn 1,2 dihydroxylation, oxidative cleavage of alkenes, with ozone, electrophilic addition of bromine and chlorine to an alkyne, addition of hydrogen halides to alkynes, oxidative cleavage of alkynes, autooxidation, alkene epoxidation, and there's a heck ton more. So so yeah, so this is my first tutorial, and stay tuned for the remainder.